10, 9, 8. We have a go for main engine start. We have main engine start. 4, 3, 2, 1, 0.
In 2027, NASA plans to launch its Dragonfly mission. This will be an octocopter that makes measurements at the surface and in the atmosphere of Saturn's moon, Titan. Titan's atmosphere is of interest because it is considered to potentially support life as well as having been through a similar evolutionary process to Earth. On Earth, rotorcraft, such as an octocopter, are less efficient than a fixed-wing aeroplane designed for a similar mission. Given the benefits of completing flights of greater range in this application, it is surprising that a fixed-wing configuration has not been strongly considered for this mission. My project has designed an aircraft for a similar profile, yielding positive results, and has found interesting differences than to designing an aircraft to operate on Earth. To begin the design, we must first understand what's so different about the environment that we're designing for. Firstly, the lift equation can be rearranged in terms of design geometry. S is the wing area and CL is the lift coefficient, defined by wing section geometry. For example, if the angle of attack of the wing section is increased, so is the lift coefficient. Titan, in comparison to Earth, has a gravitational acceleration of 7 times less and an atmospheric density of 4 times more. For a mission of the same speed and an aircraft of identical mass, this means the SCL requirement on Titan is approximately 28 times less. This allows the wing area of a design to be reduced, and therefore we also reduce the mass of the aircraft. If the mass is reduced, this means that the lift we have to generate is even less, making the flight even more efficient on Titan. Another equation to consider is the Reynolds number. This governs the type of flow that the aircraft sees. The higher the Reynolds number, the more turbulent the flow is. For a wing section on Earth, transition may occur towards the trailing edge. Here, the air has gone turbulent and as such, increased boundary layer drag is experienced. However, on Titan, we've seen that the density is 4 times greater, plus the viscosity is 3 times lower. This results in a Reynolds number 12 times higher. Let's now consider the same wing section on Titan. The transition to turbulence occurs much earlier, and so the boundary layer drag is much greater than experienced on Earth. If you sum up this increased drag across the entire wing, the need to minimize wing area becomes clear. Fortunately, the lift equation we just explored permits this on Titan. As the module approaches Titan, let's consider the aircraft's operational conditions once it takes flight. Then we can perform an initial sizing of its key components. Using the lift equation, the SCL requirement is found from defining a speed for the mission. The mission range is defined as 40 kilometers and we want to be able to cover that distance in an hour. If the aircraft is to spend about 3/4 of this time in cruise, we yield a cruise speed of 14.8 meters a second. This speed is nearly 5 meters a second or 11 miles an hour faster than the predicted cruise speed for Dragonfly. The aircraft is assumed to use Dragonfly's payload, the mass of which is estimated by comparing against similar instrumentation on board the Mars rover. Scaling a light sports aircraft from Earth to this application allows an estimate of the structural mass to be made. The overall mass of the structure and payload is predicted to be 118 kilograms. This means that 159 newtons of lift force is required. On Earth, 1,150 newtons would be required to lift this same mass. From this speed and lift force, the SCL requirement is calculated from the same lift equation. An IPython notebook is used to quickly generate geometry and test its lift against the SCL requirement. If a class is created to handle wing parameters, then automatically calculate the SCL this geometry produces, then the span or angle of attack of a wing can be changed and the results instantly seen. Taking in span, chord length and the aerofoil's sectional lift coefficient, the SCL can be calculated. We can then create another instance of this class to produce a tail which has the lift to balance the main wing, keeping the aircraft straight and stable. To perform calculations for the entire aircraft, with distances between components defined, an aircraft class relating these two wings is created. Components can be quickly swapped and the lift and moment balance change seen. The values calculated here are just a prediction from analytical methods. We want more accurate results, however, so that the designed aircraft will perform closer to how we expect. For this, XFLR5 can be used. This program takes a wing, splits it into individual aerofoils, analyses the aerodynamic results of each aerofoil, and then interpolates this across the entire wing. It also considers the influence of the main wing on the flow over the tailplane. To analyse the aircraft geometry set up in the IPython notebook, I developed a method to convert the aircraft geometry to a format which can be imported into XFLR5. This will soon be made available on GitHub should you wish to do the same. The details of this method are also given in the appendix of the project's report. 3 planforms are created in the IPython notebook. One has a high aspect ratio and area, one has medium, and one has a small aspect ratio and area. These planforms are then balanced by tailplanes and imported into XFLR5 through the conversion method. The aircraft are then analysed in straight and level cruise conditions. The smallest wing we just created was found to be incapable of producing the lift required before reaching an angle of attack close to the stall regime. The largest aspect ratio wing was shown, as expected, to have a low induced drag. However, despite having a lower aspect ratio, the medium-sized wing has a greater lift-to-drag ratio, which is a measure of efficiency. This is because its proportion of viscous drag is lower. Recall that we need a smaller area to reduce the more prominent viscous drag seen on Titan. We can then combine the benefits of the high aspect ratio with the low area to produce a more efficient aircraft. Recall that the speed the aircraft is designed for was based on a simple range and time estimate. Now that an aircraft geometry has been designed, we can select a new speed for it to fly at, which reduces the drag. Simulating this aircraft at multiple speeds reveals that cruising 0.7 meters a second or 1.6 miles an hour faster reduces the drag and therefore the energy consumption of the aircraft. The wing geometry can then be refined to fit this new speed. As the speed has increased, the SCL of the wing can decrease, allowing a smaller and therefore lower drag wing to be used. This speed increase wasn't much more, so any further speed increases would give us a negligible impact on efficiency. The power for flight is generated by a radioisotope thermoelectric generator, or RTG. On Titan, one solar day-night cycle is 384 hours. This is about 16 Earth days, half of which is in sunlight when flying operations can be conducted. Flight requires more power than the RTG can generate, so a battery must be used to supplement the power. If we assume that overnight the battery is charged by the RTG, and operations in the day consist of either flight or tasks that require full power from the RTG so that the battery isn't being charged, such as communications, we can calculate how many hours can be spent flying in one solar day. The power required for flight can be calculated from the aircraft's speed, geometry, and drag. If we give the aircraft a 5 kg battery and a 70 watt RTG, the total flying time per solar day is calculated as 11.1 hours. This means that, compared to the estimates for Dragonfly, per unit mass of battery, the designed aircraft can travel 44 times farther or spend a factor of 33 more time in the air. This prediction will reduce as prototyping produces better mass estimates and 3D computational fluid dynamics delivers updated drag results. Nevertheless, the advantage over a rotorcraft will remain. We have performed aerodynamic designs and power calculations to quantify how much farther or more endurance a fixed-wing aircraft can operate on a Dragonfly-like mission compared to using a rotorcraft. Please read the report to find out more on the operating environment on Titan, the design of a simple fuselage to house the scientific payload, and how I verified that the aircraft would fly stably, just to name a few of the report's contents. All of this research forms a basic design of a fixed-wing aircraft that I believe can be developed into a vehicle more capable than the proposed Dragonfly craft, able to take more samples and photographs from more remote areas, increasing our knowledge of Titan's ability to support life. There will also come a time where human activity on extraterrestrial bodies involves multiple bases and aircraft transporting packages between them will be needed. This research covers the principles that can be followed to design aircraft for atmospheres different to Earth's. Thank you to those who made this project possible, and thank you for watching.